Hey guys, in this video we will be going over how to simplify complex fractions. So in algebra, sometimes we encounter fractions that contain fractions in their numerators, denominators, or both. And such fractions are called complex fractions. This fraction bar is the main fraction bar of the complex fraction, and these are considered the numerators of the complex fraction, and these are considered the denominators of the complex fraction. So our goal in this section will be to write complex fractions in simplest form. So a complex fraction is in simplest form when it is in the form p over q, where p and q are polynomials that have no common factors. We'll begin by looking at two different methods for simplifying complex fractions, starting with the first method. For method 1, first step is to add or subtract the fractions in the numerator and denominator of the complex fraction so that they are both written as a single fraction. The next step would be to perform the division by multiplying the numerator of the complex fraction by the reciprocal of the denominator of the complex fraction, which is just saying use the keep, change, flip method. And the last step would be to write the result in simplest form. So let's use this method on a few examples. For the following complex fraction, in order to simplify, the first step would be to get both the numerator and denominator of the complex fraction written as a single fraction. This condition is already satisfied, so we will proceed to the second step. So we will perform the indicated division by multiplying the numerator of the complex fraction by the reciprocal of the denominator of the complex fraction. And the reason we can do this is because this complex fraction can be written as division horizontally, thus keeping the first rational expression the same, changing the division to multiplication, and then flipping the second rational expression to its reciprocal. And now we multiply as normal. So the numerator and denominator do not have a common factor to divide out, so multiplying across, our answer is 15 over 16. So now our complex fraction is written in simplest form. For the next example, again notice how the numerator and denominator of the complex fraction are already written as a single fraction. Therefore, we can skip to step 2 and perform the indicated division. Again, if it helps, we can write the division problem horizontally. Now we need to change to multiplication by multiplying the first rational expression by the reciprocal of the other, using keep, change, flip as a guidance. And again, we only use this rule whenever we are dividing. Okay, so before we multiply across, let's see if we can divide out any common factors. Let's factor this numerator. We can factor out a GCF of 7, and now it looks like we can divide out the common factor x minus 4. Multiply across, and we get 7x over 3 as our answer. And we have simplified our complex fraction. For the next example, this time we don't have the numerator and the denominator written as a single fraction. So let's start with the numerator. In order to write them as a single fraction, we must first add them by finding their common denominator. So the least common denominator of 2 and 3 is 6. And to rewrite these fractions as an equivalent fraction with a denominator of 6, we multiply this fraction by 3 over 3 and the other fraction by 2 over 2. Now that we have the same denominator, we can add their numerators across while keeping their common denominator. And now the numerator of the complex fraction is a single fraction. Now let's do the same for the denominator of the complex fraction. We can write 3 as 3 over 1 and find their common denominator. So the LCD of 1 and 4 is 4. So multiply this fraction by 4 over 4, and the other fraction is fine since it already has a denominator of 4. So now we subtract their numerators while keeping the common denominator, and now the denominator of the complex fraction is written as a single fraction. So let's rewrite our complex fraction. We have 5/6 over 7/4, which is the same as 5 over 6 divided by 7 over 4. And now we can use our keep, change, flip rule by multiplying the first expression by the reciprocal of the second expression. And it looks like we can divide out a common factor between 4 and 6. If it helps, you can write these as factors with the GCF of 2 being one of those factors. Divide out the 2, and now multiplying across, we get 10 over 21 as our answer. So this is what our complex fraction simplifies to. For this example, the numerator of the complex fraction is already written as a single fraction. However, the denominator is not, so we'll have to work with the denominator of the complex fraction and write it as a single fraction. So the least common denominator for y and x will just be y times x, or x times y. To rewrite these fractions as an equivalent fraction with a denominator of xy, we multiply this fraction by x over x, and the other fraction by y over y. And now that we have the same denominator, we can subtract their numerators while keeping the common denominator. And now the denominator of the complex fraction is written as a single fraction. So our complex fraction is now the following. And we can write this horizontally as 2 over x squared y divided by x minus y squared over xy. Now we can use our keep change flip rule by multiplying the first expression by the reciprocal of the second expression. And now it looks like we can divide out a common factor between x and x squared. And if it helps, you can write these as factors with the GCF of x being one of those factors. So we can divide out the x's, and we can also divide out the y's. And now multiplying across, we get 2 over x times x minus y squared. So this is what our complex fraction simplifies to. There is another method we can use to simplify complex fractions that may be a little faster to work with. So for method 2, the first step would be to find the least common denominator of all the fractions in the complex fraction. And the next step is to multiply both the numerator and denominator of the complex fraction by the LCD. And the last step would be to simplify the result. So let's try the same examples using this method. So this time, we will simplify the complex fraction using method 2. The first step is to find the least common denominator of all the fractions in the complex fraction. So the least common denominator of 2, 3, and 4 is 12. Now we multiply the numerator and the denominator of the complex fraction by this LCD. Distribute the 12 across and simplify. And this reduces to 6 plus 4 over 36 minus 15, which equals 10 over 21. Our result is simplified, and this is our final answer, which is the same answer that we previously got using method 1. And for this example, again, we will simplify using method 2. So we need to find the least common denominator of all the fractions in the complex fraction. So of x squared y, x, and y. And if it helps, we can always list out the factors for each denominator. So our least common denominator will be x squared y. We multiply the numerator and the denominator of the complex fraction by this LCD. Simplify, and we get 2 over x squared minus xy squared. And the last thing we could do is to factor a GCF of x from the denominator. And this is our final answer, which is also the answer we had using method 1. Let's try another example. So to simplify this complex fraction, let's use method 2. First, we need to find the LCD of all the fractions. So the LCD of the denominators 2x plus 1, x plus 3, and 2x plus 1, which we already have, will be 2x plus 1 times x plus 3. So now we multiply the numerator and denominator of the complex fraction by the LCD. And simplify. Then we simplify the numerator and denominator by multiplying and combining like terms. And now we just check to see if our rational expression is in simplest form. We can factor the numerator by factoring out a GCF of 2. And then we can also factor out a GCF of 10 in the denominator. We can now factor this trinomial, and we can divide out a common factor of 2 between 2 and 10. So our final answer is x plus 3 times x plus 3 over 5 times x plus 1, which is the same as x plus 3 quantity squared over 5 times x plus 1.